The problem we are going to study now is definitely on the more advanced side, but at the same time it is a quite famous one. It is due to Conway, a British mathematician, and you can find lots of information about it on Wikipedia, both about Conway and about the game of life itself. In this game, we're kind of simulating life, what life would be in a cellular automaton. What does that mean? Imagine that we have a grid, and m times n grid, and then each square of the grid has a cell. Now, each cell can either be dead or alive, and we have rules that say what conditions make a cell dead and what conditions make the cell alive. Based on the initial configuration of which cells are alive and which cells are dead, then the game will progress on its own. So we don't really have to do anything other than give the initial configuration and program the rules based on which the grid will be changing on which cells are dead and which cells are alive. Now, as you can imagine, each cell will have 8 neighbors, and based on the properties of these neighbors, whether they are dead or alive, the cell's condition can change. Here are the rules of life on how a cell can change its condition. If we have an isolated cell, if it is the only alive cell among its neighbors, then it will have to die as well. Now, if 4 or more cells around it are alive, that will also lead into its death because of overcrowding. So we have already seen 2 conditions that will lead a cell from being alive to being dead. If 2 or 3 neighbors are alive, and not more than that, then the cell will be at a stable condition and it will not change. The very last rule is the one that will make a dead cell alive. And again, you have to look at the cell that is at the very middle of the box. If the cell has 3 neighbors that are empty, that will give birth to that cell. And on the right, you see that the cell has now turned blue, which means that it is alive. Based on the rules that we just mentioned, you can see a few patterns that can arise. You can see on the very left column still lives, steady situations that will not change. But what is probably more interesting is to see the oscillators. Take a look at the blinker, for example. It has a period 2, which means that once it is vertical, then at the next time it will be horizontal, and after that it will repeat. So that's why the period is 2. Again, through Wikipedia you can take a look at several different patterns and spaceships, and then be more motivated to actually implement the program that will be implementing this game of life of Conway. Like with the deck of cards, you can find the solution to the Conway's game of life by Dr. Tim Korb on this URL. This example is taken from the Start Concurrent book, and again you are very highly recommended to try to implement this game yourselves before taking a look at the solution.